particular spot. I also have to, it's not usually a good idea to admit that you're not feeling your best, but I am definitely not feeling my best. I've got a gratuitous movie up there I'm not going to refer to throughout the talk, but since Romain Tessier is in here, I had to put a gratuitous AMR simulation there to, since he is sort of the contemporary godfather of AMR from my perspective. Okay, so I was asked to talk about, well, you can see the title in there, I think it was Mass Assembly and Metal Enrichment. Now, after 4 days, everything I wanted to say has already been said by people who are more knowledgeable than I, and I look at the people coming after me who are more knowledgeable than I. So what I've done is I had sort of sat back yesterday and tried to think what could I actually talk about that would be new. And so I took the 18 SOC members, looked at the 1,000 papers they published over the last 5 years, and took their abstracts of about 600,000 words and ran it through a word cloud just to see what came up with. And so this is what the SOC is interested in. Some things just to take from this. The SOC is more interested in spectroscopy than photometry. Emission way more than absorption. In terms of the scales that they worked on, you can see kiloparsecs, and you can see it sort of dropping down on either side, megaparsecs and parsecs. There's a few on the SOC who are interested in AU scale and even gigaparsec scale, so that's kind of interesting. There was less on the IMF than I had thought. There was more on dust and extinction, and a large number of occurrences of the word sunspot. Outflows, much more interesting than inflows at the SOC. If you break it down by components, you can see disks, halos, ellipticals, ISM, voltages, and bars to see the distribution of the SOC's interest. And in terms of the words like mass, metals, kinematics, luminosity, and color, you can read the numbers there. So metals are an important part of what the SOC is interested in. Not so much on yields, the actual stuff that goes into metal enrichment. So I will say something at the very end if I've got a couple minutes to spare. Okay, so in some sense my title has been rearranged a little bit to reflect some of those things that you saw there. So you've seen this sort of galactic archaeology slide from Simon Lilly and Co. a couple of times, so I'm not going to belabor the point. What I'm going to do is I'm going to look through the different components that you can see in this image, starting from the ultimate fuel reservoir, the IgM, how it passes into the halo, gets into the disk, and the roles of outflows. But I'm not going to be talking about mass. I'm going to be talking more about how the metals get moved around, not only from an external sense in terms of infall, outflows, the IgM, but also internal metal reassembly. And we've heard some of that in various talks in relation to abundance gradients. I will touch very, very briefly on things like stellar migration and radio gas flows. They're things that we've not really talked about, and I just want to note them as something that's important for metal reassembly, if you like. And so this is the outline. I'm only going to do a couple of slides per topic. As I say, it's less of a coherent review and more just sort of dipping into a few different things that we have heard about and a few different things that we've not heard about over the course of the week. So I'll start off with just the IgM. We know that there are metals in the IgM. Us who do modeling, we normally think of the IgM as being pristine or metal-free. I'll come back to that in just a second. But we do know that obviously there are metals in the IgM. We've known that for more than 50 years now. It's a classic spectrum from Burbage and Co. And over the last 50 years, obviously, we've had things like HST, fused, and ground-based complements. We've built upon those first rough numbers in terms of the metal content, the barium content of the IgM, and this is from the early 90s, so 25, 30 years, we've known that it's not just scaled solar abundances as well in the IgM, and so what we say broadly called alpha enhanced. And again, there's a whole literature from, especially with HST and fuse, that has looked at the abundance patterns in this IgM gas. If you take a compilation from Enrique and Brugeval et al., this is, on the left is high density gas. This is more the diffuse IgM, and the diffuse IgM also has a floor. It's not zero, it has a floor. It's down at sort of 0.1% solar metallicity all the way back to redshift 6, probably beyond. So again, metals in the IgM, that's something to remember. It doesn't enter into halos, it's pristine. So what is the local analogs? We had a nice talk from Mary Putman high velocity clouds are sort of the local analogs of this infalling gas, and some fraction of it probably is. This is the classic map from Bart Wacker showing the distribution of high velocity clouds across the sky. The most famous of the high velocity clouds in the top right corner, the Magellan Extreme. This is what I worked on with Mary during her PhD. It's just something to remember. A takeaway point is that if you convert it into mass, the Magellan Extreme is about 99% of in terms of the neutral hydrogen, the 21 centimeter hydrogen, 99% of the anomalous velocity gas in the halo. Only a few times 10 to the 7th is tied up in these high velocity clouds that cover sort of 40% of the sky. Their metallicities are around quarter so the metallicity, as Filippo was talking about yesterday. So how does that fuel actually reach the disk? I can just take a step aside for a second and just say a couple words about classic sort of analytical galactic chemical evolution, the sorts of things that I did earlier in my career. This is how you can sort of boil chemical evolution down to one single equation. And it's the rate of change of the gas mass, or if you want, you can replace that with an individual isotope if you like. And there's 4 terms there: depletion due to star formation, and a gas outflow term, and a gas restitution term, and an accretion term, A. And so what we do in chemical evolution is we take those equations and we apply them in individual zones. If you think of a disk galaxy, we split it up into annuli, and we run that equation over each of the annuli independently. But the only thing that we adjust is the functional form of that accretion term A. And that's how we control the growth of the disk in an inside-out fashion. You can go through the literature over the last 20 years or so and find different functional forms for how the disk should be growing. Some of them grow as, this is a compilation from Mercedes Moya, as a function of radius, how this infall time scale varies as a function of radius. And some of them are linear with radius, some of them have a very steep dependence with radius. But there's essentially no empirical constraints on what this functional form really should be, or more importantly, what I'll say in the next couple of minutes, the direction of this infall. Those classic chemical evolution models are 1D. It doesn't tell you how the gas gets in there, whether it comes in radially, drops down on top of the disk, it just appears as part of this 1D term, this accretion term A. So I'll just skip to this one. So in terms of figuring out how the gas gets in and the direction that it gets in, we have, until very recently, drawn upon simulations to figure out what the orientation of this gas is as it comes in. One quick test that we did using a simulation that the chair ran back 7 years ago or so, using Ramsey's. Romain was involved in that as well. It's a cosmological Milky Way scale disk that we basically just tracked where the gas came in, working at the mass flux as it enters the disk for the first time, and just looked at what the time scale that gas arrival was as a function of radius. And that's what's shown on the left here, split up into 3 different radial bins. And the inner radius is a more rapid time scale, and the outer radius a longer time scale. And that's more or less exactly what you see in the classic analytical model. So without any fine tuning, the disk is growing in an inside-out fashion. Perhaps that's not shocking, but it was nice to see that it was appearing at the same sort of functional form, the same functional rate as we were getting in the classical models. Something about this simulation, though, is that the gas was actually effectively, to keep it simple, dropping more or less down on top of the disk, rather than being fed in through the plane. So this particular simulation was similar to what Mary was talking about in the context of M33, her picture of a big pile of gas that was more or less dropping down on top of M33. So it's sort of consistent with that picture. The reality is not quite like that. It looks like from observations, and certainly if you go to the back of the room and look, I think it's poster 33, Glenn's poster. That's a beautiful piece of work that uses background magnesium tube absorbers around halos and looks at how the gas is actually distributed around halos. You find it's bimodal, and it looks like it's consistent with a picture of outflows sort of going out of the disk, as you might think, orthogonal to the disk, circulating around and being fed back in through the plane. And the simulations that we've been running lately, and I suspect many of the simulations that others in the room are doing, probably would find something very similar. And there's excellent constraints observationally, not only just in the orientation, but in terms of the kinematics and the metallicity maps that Glenn and co. have actually are putting out now. So I would encourage the simulators to look very carefully at this sort of work when you're trying to transform into the observational plane. So what does the outflows do to this gas that's falling in? We know that strong feedback pushes metals further out. And whether you are looking at, say, this is neutral hydrogen up here, this is oxygen 6 down here, column density maps for low feedback and high feedback. So if you just look at the oxygen 6 is getting pushed further out into the halo. You have this circumgalactic medium, it's shock heated to 200,000 degrees, and you see this substantial rise in the oxygen 6 as a function of radius. And you can go out and compare this with observations from the Jasons, Tumlinson, and Chaska. And what you find is that if you look at the absorbers as a function of impact parameter, when you use strong feedback, whether you're looking around an L-star galaxy or a dwarf galaxy, you naturally find that the simulations lie right on top of the observations without any fine-tuning in these particular suites. And so this is, again, a nice independent test of whether the subgrid physics that you put into your simulations is actually feasible or not. And again, this is something I would encourage the simulators to confront their simulations against. One other thing in relation to that circumgalactic medium, if you really beautiful work from Nicholas Leonard et al. If you go and look at how that oxygen 6 is distributed, not necessarily as a function of radius, but as a function of metallicity, what you find is it's not uniform metallicity, the corona. What you find is that it's actually quite bimodal. There's a peak around 2% solar, and there's a peak around 40% solar. So this gas, it's being fed in through the intergalactic medium, and it's getting mixed with this outflowing material. This mixing is occurring in a way that leads to a bimodal distribution of the oxygen in the corona. It's not uniformly mixed. So again, this is all the way out to sort of 150 kiloparsecs or so in terms of impact parameter. So I did this morning or late last night, I took one of our simulations to see what it actually looks like. We do get something that's bimodal, and this peak down here is associated with the fountain material that's being pushed up, and this is material that's lower metallicity that's sort of populated throughout the halo. It doesn't match exactly. We don't get any of this metal-rich component beyond about 30 kiloparsecs or so, whereas observationally, again, you see it out to at least 150 kiloparsecs or so. So if you want a nice, interesting data set to confront your simulations against, this is a good way to go about it. Let's see. In terms of this links back to one of the talks earlier on the fire simulations. In terms of the time scale for this mixing that's going on, again, one thing you can do with the simulation is you can trace the material, and especially with these SPH simulations, it's very easy to trace the gas particles. So you can look at the infall rate as you cross the virial radius, and the infall rate as you sort of enter into the star-forming region close to the disk. And there's 6 different simulations, color-coded by metallicity. Blue is low, red is high. And so you can see as gas crosses the virial radius, not surprisingly, it's lower metallicity. As it enters the star-forming region, it's been enriched by this interaction, this turbulent mixing with the material, the outflows that's coming up into the halo. One of the things that you can do is you can look at the time scales for gas, for example, to cross the virial radius and enter the star-forming region. Then you can track the gas particles into the star-forming region and see how long it takes before they get incorporated into star formation. And then you can track the gas particles when they get returned back into the interstellar medium or into the corona for them to recycle back into the star-forming region. And you can make a plot showing the different time scales of each of these components. And what you find is, I know someone right on the very first day that said that everything is not exponentials, but I'm going to go ahead and do that anyways. You fit exponentials to these time scale distributions, and you find that something on the order of a gig-a-year for gas to come from the virial radius into the star-forming region. Gas spends about 4 giga-years in a time scale, and it's sitting within the star-forming region, and then there's a giga-year time scale to recycle. Again, this is the sort of thing that you can do with simulations. Okay, I want to just spend a few minutes, just check my time here, spend a few minutes on what happens once the gas is actually inside of the galaxy. And there was a hint of it just in that last slide when I said that it's about 4 giga-years or so in these particular simulations that I was alluding to for gas once it gets into the star-forming region before it actually gets incorporated in star formation. And that's because star formation is not particularly efficient. We had a beautiful talk from Ian Bennell that went through the details of that. And so one thing I do want to say is once gas gets into the halo, gets into the disk, Okay, say it's there for a few gigayears or so. It doesn't just sort of drop into the disk and just happily necessarily just move around in a nice circular orbit and stay where it dropped in. Gas has a tendency to move. It's got velocity dispersion, but there can also be bulk motions. It's very difficult to actually measure whether there are bulk systematic radial flows, because we're for the Milky Way, obviously we're sitting right in the middle of it. This is probably a paper that no one in the room has read. And certainly from looking at the citation rate, no one in this room has cited it. It's a little-known IAU paper from someone in Bonn who pointed in the empty center of the Milky Way and very carefully stepped around and tried to take into account the uncertainties associated with the local standard of rest to see if there was any evidence for any bulk systematic radial flow in the gas. And what they found was, it's a very difficult measurement, and I'm not sure whether to believe it or not, but suggested that it was consistent with the kinematics of the gas was consistent with an inflow, a radial inflow from the outer disk inwards of about 3 kilometers a second. Now, it doesn't sound like a whole lot when you think of velocity dispersion, but one of the things I like to remind sort of first-year students as well is that, remember, 1 kilometer a second is about a kiloparsec per gigayear. So radial flows of a few kilometers a second can move gas around if this is actually the case, if this observation actually held up. You can try and step out and look at extragalactic systems, and there's a pretty comprehensive literature. There's Leo Blitz and Tony Wong, Sharon Mike. These are just a couple that I pulled from the recent literature showing what for example, down at the bottom here is M57. This is only the inner sort of 4 or 5 kiloparsecs, but showing you're looking at various streaming motions here associated with different co-rotations. But you are seeing a decomposition of the kinematics into a radial component, which is down here. So the inner part of the disk, there's minus 10 to minus 20 kilometers inflow at that sort of rate, 10 kilometers a second. If you look at this compilation from Tony Wong, then you see what the maximum radial flow is, and it ranges from consistent with more or less 0 up to an outflow at 56 kilometers a second, an inflow of 56 kilometers a second. This is also M57, but it's over the outer part of the disk. So I'm just putting up those as numbers. Again, this is the sort of thing that you can look at inside of your simulation. Do you get radial flows that are consistent with that? My quick look at our simulations is the radial flows are too high. They're not consistent with that. That's, again, just something to think about. And in terms of radial flows, you're not just moving gas around. Of course, that gas carries metals, so you're moving metals. And so again, one of the sort of tests that people should be thinking about is the metallicity distribution in the gas similar to the metallicity distribution in the stars? If the gas is moving by, if there is some sort of systematic flow in the gas, then you potentially are flattening the metallicity gradient. So is your metallicity gradient in the stars similar to what you see in the gas? There's a lot of work being done in Khalifa. There's posters at the back that address some of this. This is just a comparison of the mean metallicity in light in the stars and the mean metallicity in the gas from Patricia from the chair and Hacho. Data quality is not particularly great, but it shows you the sort of thing you can do. In this particular case, in the centers of these galaxies, there's no apparent correlation between the gas and the stellar abundances. This is a good, challenging test that you can confront your simulations against. It needs a better observational data set against which to compare, but it's a nice thing to look at. So what happens to the stars that form from this gas, from this fuel? Just one slide on this, because there's an entire IAU symposium that gets based around this concept of stellar migration or radial migration, and what the physical or numerical mechanisms are that are responsible for moving stars from one particular orbit to another particular orbit, bar-driven resonances, spiral arm-driven resonances, etc., etc. These are just, if you look at the top panel, this is from Rosker, using idealized simulations. It's just a plot showing the final radius versus the initial radius. When you move to the outer part of the disk, you find that the stars have migrated on average in their idealized simulations by, say, 3 or 4 kiloparsecs from their birth location. Cosmological simulation that, again, the chair had run, sent to Blasquez et al. 2009, found something similar. Physical mechanisms are not necessarily the same, but the stars do move on average, say, a couple of kiloparsecs from their birth location. So again, when you're thinking about comparing stellar gradients versus gas phase gradients, these are the sorts of physical things that you need to keep in mind, as I think Vladimir hinted at in one of his questions yesterday. And so what is the time evolution of this behavior? Now, again, this was actually what I was going to talk about primarily, but because it was covered so nicely in both of the Patricia's talks to Sarah and Sanchez Vasquez, I'm just going to do this very quickly. Again, the time evolution of the gradients is a really excellent way to confront your simulations. This is a plot showing the redshift evolution of the oxygen abundance gradient for a wide range of simulations, half dozen or so different simulations, as well as a suite run with Ramses as well, some analytical models up here. Here's where things sit today, normal disk galaxies. This was the first point at high redshift from Lisa, from Juan et al. And what you find there is that most of the simulations and models end up over here. That's the boundary condition, so in some sense you know they're going to get it right. But they get there in very different ways. And so empirical evidence at high redshift is incredibly useful and very powerful for constraining the degree of feedback. And again, as this was commented on in Patricia's talk earlier, weak feedback, call it weak conservative feedback, let's say, has a much more dramatic time evolution of the radial abundance gradients. Stronger feedback, enhanced feedback, has a much more gentle evolution. And so the models run with strong feedback are consistent with most of the observations. Now, there were the first few lensed determinations of gradients. 3 of the 4 were quite steep, but when you look at the samples now, these seem to be more the outlier than the norm. I encourage you to go look at that paper there. I think I will skip over the mass dependency because this effectively is exactly what Patricia Teixeira showed yesterday. We find exactly the same thing that she found in her simulations. So I want to end with 2 random things, just in passing. The first is feedback is hard. Most of the simulations I've shown you, most of the ones that you've seen thus far, tend to put feedback with subgrid physics wrapped up into supernova, some either thermal or kinetic feedback associated with supernova. But we know if you believe in, say, equipartition of energy in the interstellar medium, you got roughly an electron volt per cubic centimeter associated with thermal energy. You've got an electron volt per cubic centimeter associated with magnetic energy and with cosmic rays. These are things that are not in the simulations that I've shown you. But they do have an impact, and there are simulations out there. So it's something to remember when you're thinking about the simulations and the subgrid physics. This is missing physics in a lot of the simulations that are available now. Roman will probably show some things with MHD, but that's just to give you a hint. I'll skip over cosmic rays other than to say, much like the magnetic fields, they can play a very important part in terms of driving galactic winds and outflows. They work on a different time scale than, it's a non-thermal component, so it works on a different component, a different time scale than the thermal component. Now, and I wanted to just say something very quickly about nucleosynthesis, just in one slide. Give a whole talk on, but I'll just do it in one, because it links back to one of the nice results we saw in Chiara's talk on the first day. It was for M87, shows really enhanced sodium to magnesium, a factor of 2 or so above solar. Now, what I did last night was just take the Amanda Caracas AGB yields and Kiefe Lamonji supernova type 2 yields and just plot what the ratio of sodium to magnesium is as a function of initial mass. And this is where, this is what it looks like. This is where the M87 value sits. And so, if you do the same thing with the new grid yields from Marco Pignatari et al., which is sort of a more self-consistent stellar evolution, nucleosynthesis, and reaction rate code, this is what it looks like here. This is where the observations sit. So this is just one abundance ratio of sodium to magnesium. In this case, it'd be very easy for me to run a model and get enhanced sodium to magnesium using those set of yields. But if I did the same thing with the new grid yields, it would be much more difficult. You can start playing games in your head with convolving that with an IMF to figure out whether it would be easy or not. But it just shows you that there are still big differences between the nucleosynthetic yields that are out there, and be aware of that when we're talking about metal enrichment and how you incorporate that into your chemical evolution code. So I'm down to 1 minute. So that was going to be where I ended, but I want to, I'm just going to spend the last 1 minute showing you something, a bit of history, I guess, in terms of detecting metals outside the galaxy. When I started to think about how I was going to review this, I started thinking about mass metallicity relations, and I started to go back through the literature. But then I saw that a lot of other people were talking about things like that, so I decided I wasn't going to go down that road. But I had gone through the literature quite far back, and I think one of the speakers on the first day quoted Hubble 1924. So I wanted to see if I could find a legitimate way to beat that in terms of history. So we normally think of the Pugh-et-al. as maybe the first acknowledged sort of pioneering studies of extragalactic metals, at least in a sort of statistical sense. And that's, and given the location where we are in Mexico, it's very good to highlight that. And this is their prelim, that's the mass metallicity relation based on the data set that they had at the time. Maybe the first sort of 100% definitive determination of metals outside the galaxy, traced to Searle and Sargent. You can go back a little bit further to Manuel's work. I think that this is really, to me, sort of 99% definitive determination of metals outside the extragalactic metals. It was couched in a way that allowed some temperature variations to explain it, but I didn't put it down as 100%, but I put it down as 99%. Go back a bit further, Burbage and Burbage hinted at it, but they didn't really believe that what they were seeing were metallicity differences in external systems, but they thought that the explanation was more likely to be to different excitation conditions. So I just got a couple more that's kind of interesting, but if you go back to, there's obviously a long history of detecting lines, extragalactic lines, not doing any sort of chemistry with them. Really nice work from Aller in 42. Obviously, you go back to Slipher and back in 1917. But I've just got just a couple more. This is the Julius Scheiner from 1899. This is the sort of claim credit for the first detected extragalactic lines. There was no spectra presented in that particular paper. It's just sort of described down in here. So that was interesting. About 10 years later, Edward Pfaff came out with a paper and he dismissed this detection and said it was scattered light. It did present the spectra, you can see NGC 1068 down here and Andromeda up here, but basically concluded that there was some doubt as to the interpretation, because I guess he wanted to take claim for it. So what I found, this is just a couple of days ago, and it was kind of interesting. About a month later, Julius Scheiner posted a rebuttal that was published in AppJ, and it was full on in terms of tearing into Edward Pfaff. So I've highlighted a couple of the good points regarding, the normal procedure would have been to consult me. It's been more intelligible. Fantastic, short, to the point thing that AppJ would never publish nowadays. One thing in passing about Edward Pfaff is that here's an interesting paper that Pfaff did around the same time, was the use, and just read the title there, the use of astronomical telescopes in determining the speeds of migrating birds. Fantastic little paper in Science, using two telescopes, two astronomers using basically parallax and standing at different places on campus and yelling at each other when they saw birds enter into their eyepiece. Fantastic. Great little paper. Anyways, and so this is the last slide, actually. This is what I think really is the first detection of extragalactic lines in a spectra from William Huggins in 1864. It's a fascinating little paper that you can find on AES, and I forgot to put on the page, but basically didn't see anything in M31, but this thing here, which is talked about a very, very bright and large and round. If you go through Wikipedia or read through the history books, this is thought to be M31, but in fact it's actually M32. I had to go through and figure out north polar distances because they didn't use declinations back then. They used the opposite of declination, NPD. So it took me a while in NED to figure out where they were actually pointing, but that was actually M32, not M31. But regardless, first detection, with a spectrum, extragalactic lines. That's all I want to say. Oh, wait, there was one thing. No. I have a postdoc, so I know Adam, I'm not sure if you're in the room, but I'm looking for a postdoc right now to help me on some of the simulation work and chemical evolution work. Thank you. Okay,
we have 1 minute for questions.
Yeah, thanks. I'll take that job. So, in the galaxies where there are observed radial inflows in disks, are there equally observed radial outflows, and do they balance such that angular momentum is conserved? My impression is that must be the case, but just wondering if there's empirical evidence of that.
There's empirical evidence. Well,
is there?
In this, in the simulations, that's exactly what we find.
Well, yeah.
Yeah.
I mean, the simulations are
So,
going to be perfect always, so.
Yeah. That's true. But I observationally, if Glenn's in the room, he might know the answer.
Okay, other questions? Tanya?
I want to pick up on the last point about sodium amendments that you made, which is very interesting. I'm actually, as far as I know, but I wanted to ask you what you know about it in the Milky Way. So halo or disk stars, actually, there's no sodium enhancement observed,
Yeah.
which kind of goes in line with the yields you described. So it's really odd if you find sodium enhancement in other galaxies, because there's no way, there doesn't seem to be a way to make it.
Well, I agree 100%. 100%. It would be, you have to do something very strange with the model to force that, and I mean, I couldn't do it. If I ran the chemical evolution model using those particular Kefi-Lagrange yields, then I'm going to overproduce sodium. I can't simultaneously do M87 and the Milky Way at the same time, even taking into account metallicity-dependent yields and things like that. So, yeah, I don't have a simple way to do that.
Okay, thank you. We have to move on, right? So let's then wrap again.